Okay, so this is a big topic, and this will definitely take us the rest of the day. We'll take a break in like 15-20 minutes. And this topic is on auth and auth, which is a big part of your iteration too. And why is it called auth and auth? Because we're talking about two topics that are super important, and these are not like, these essentially tie into topics surrounding security in the largest sense. So this is kind of like us dabbling into concepts of software security, though we do it in a very light way, and the main purpose is for you to be cognizant and slightly familiar with these concepts so that you can basically apply this and learn more. Maybe you'll get more interested in some of these topics. So let's talk about auth and auth. So the first one is authentication, right? There's two concepts, authentication and authorization. Now, authentication is the process whereby we're going to verify the identity of a user, right? Now, you've probably all been authenticated at some point. Maybe you go to some kind of venue and they ask for your ID. You go to an airport and they check your passport or something like that. It's pretty much the process of making sure that you are you, right? That's what authentication is. Authorization, on the other hand, is a process of verifying basically your privileges and like assuming that we've already figured out who you are. It's a question of like what can you do, and these two concepts are quite closely related. So if you're kind of sitting there being like, oh, that kind of sounds like the same thing, then don't worry too much about it, because we'll talk about them separately. Okay, so authentication. This one's actually probably easier for you. And you think about it, right? Like some groups might have taken this further already, but when you build your UNSW Dreams application, how do you register users? Okay, the way you might register users is by essentially they register, you collect their email and their password, and you store both of those in a dictionary somewhere, and then when they try and log in, you compare their username and password in the dictionary to what they entered, right? Like, how many groups have done that? I assume a number of those groups have done that. And we can actually have a look at an example of this, right? I'm going to open up the week 5. Week 5, oh yeah, here. And you'll see here that we actually have a file called auth.py. So let's have a look at auth.py. So we look at auth.py, and this is a, oh, I feel like that's the updated one. Oh, that's not good. Damn it. All right. Give me like just 30 seconds. I think I... Hi everyone. So I have a hilarious story for you, which is that when I noticed that the code was wrong, I paused the lecture recording and I forgot to unpause it. So that was never recorded. But so what I'm going to do is I'm going to give a quick 60, 90-second crash course in this piece of code, which was what we spent that whole time trying to get. And for anyone who's interested on the record, like when you're watching this recording, there'll be a link in the description to the actual like live recording, if that makes sense. But I really don't think it's that exciting. Because you can actually see this quite plainly, which is that we have a Flask server here, which has, and we're using a data, because you're familiar with like storing data from iteration 1. And we have a register route, which we can call with ARC. And all that happens with that register route is we pull a username and password out of the JSON payload. And then we store it in our user data. And I'm printing that out each time so that you can actually see it. So if I start this file here, this server, auth.py, and it runs on 5000 and I call register with 5000 and these details, what happens is it works, right? I actually register myself, and you can see every time I call this, I'm printing out data. In fact, if you want, what I'll do is I'll print out both data after and data before, right? So we'll just like restart this. And then when I run it, you'll see that before my function runs, my user's data is empty, and afterwards I have this dictionary here with the name. And then if I add another person, which again is like Claude Sun, then before it's just me and afterwards it's someone else, right? Which is like 2 dictionaries here. So this is all fine. This makes sense. It's like auth register. It's like that without the checks. But again, the problem here is that we are storing the password, right, as what we would call plain text. And what we mean by that is that a developer or a malicious person can actually see the password that's been entered, right, when we store it. So we're storing this password here, and maybe this is stored in a file, maybe it's stored in a database, but we don't want to store that raw password because that's dangerous, right? Because this has happened in the past as companies get hacked or other services get hacked, and a bunch of people are storing users' passwords just as ASCII characters. And we don't want to do that, which comes into this topic of authentication, right? So it's like, what's wrong with auth.py as it is, right? Not a lot. I mean, not a lot except the authentication problem to start. Now, to solve the authentication problem, we have to create a hash, right? And again, this is not a security course. This is not a maths course. There's a lot to do with hashing. But essentially, the idea of hashing is where you can take a string in Python or pretty much any language, and you can turn a normal string like, you know, Hayden Smith, my password, into a whole bunch of gibberish. And that whole bunch of gibberish can't be decoded. It's, again, without going into like the finite mathematics of it, it's essentially a function that's really easy to do in one direction, but you can't really reverse it. Now, you kind of get functions generally, right? Like maybe you have a function like, you know, def square, where it takes an x and it returns like x to the power of 2, right? But you know you can reverse that, right? Like if you get the result, you can just call, you know, square root, which will return, you know, the square root of x or something like this, right? Like you can reverse these. Most things you do are reversible. The thing about hashes though is that they're practically not reversible for all reasonable senses of them. So, and let's actually look at this together because it's a really straightforward example. I have this file here called hash.py, and what I'm going to do is I'm going to run it, and you can see that I've commented out a few of the lines here, right? So I've only included import hashlib and then this line here. And all this line is really doing is trying to convert my password to a hash. So if we run this, python3 hash.py, it spits out this. So what this is saying is this is my specific hash of this string. And if I change this string to something like, you know, polywaffle pancakes, then I'll get a different hash. And you see all these like random numbers are very different. If I do Hayden, I get a different hash, and I get a different hash for every string generally. So all these different combinations and permutations of strings have essentially a one-way function, right? I can convert from string to hash, but I can't convert from hash to string. There is no hash, there is no like reverse hash function. It just doesn't exist. So it's not really possible. And this is like a fairly fundamental principle surrounding cybersecurity, right? Is that there are these functions that exist which you can't reasonably reverse. So if you start with a password and you hash it, you get some huge string. And if you start with this huge string, you cannot mathematically just reverse this very easily at all, right? Now, what's useful about this is that storing something like this is a lot more secure than storing the actual password, because if someone gets this, it might be hard for them to decode it, right? Because remember we said you can convert from, your plain text to a hash, but you can't convert from your hash to plain text. And you can do hashing online, right? If you just Google like SHA-256 hash, there'll be like a website, right? Like something like this. You can just type in like Hayden, and you see that it spits out this number here. And you notice here that this FE28F9 is actually pretty similar to FE28F9, right? So as people are talking about in the chat, it's deterministic, right? Like a particular string directly maps to a particular hash, right? So whether I do it on the CSE machines with Python or whether I do it on this online website, every string will always turn to the same hash though, right? And I'm getting questions like, is transmitting this hash information safe? It's like, it is safe because there's no reasonable way to reverse a hash. Like if someone just gives you a hash and they say, what was this originally before you hashed it? Again, just based on the mathematics surrounding it, it's not feasible for you to actually reverse this. It's not feasible for you to do it in the other direction. Which then leads to the question of how do people basically break passwords? And like I'll show you this. If I Google like SHA-256 reverse online, right? You might think, oh, okay, I can reverse this. And it says I might paste in this hash here. Bam. Decrypt. And it tells me it's Hayden. Okay, so why is this bad or concerning? So the way that hashes work is that when people want to break passwords, when people want to reverse hashes, you can't reverse the hash. But what you can do instead is you can start randomly finding the hashes of all these different things. Like imagine you and I literally, I'm just going to open Excel right now on my computer. And like we're just going to start noting things down. We're going to be like, all right, well, Hayden is this. And then I'll say, what you'd actually do is you'd actually go to something like this and you'd say Smith. Okay, that's Smith hash, like that. And then you go here and you say like, what's Claude hash? And you store that as well, like this. And I saw, what's the Sun hash? And I store this as well. And this is where we get into this area which, people refer to as like rainbow tabling, which is basically like you just start going through every possible like password that exists and you find the hash of it. And then you store a list of hashes, and then therefore when you get a hash, you can just reverse it. But you're reversing it not because you actually can reverse the maths. You're reversing it because you kind of know what like these equate to, right? You're actually like not calling a function. You're literally just like looking things up in a giant database, basically. And this is one of the reasons why you want long passwords, right? Because if you have a long password like polywaffle pancakes, watch what happens when we try and decrypt this one. It says this hash is not in our database. And why is that? That's because the longer a password is, the more possibilities there are of different things. So what I mean is like, think about this, let's say your passwords are just letters and just letters, A to Z, lowercase. You have 26 possible passwords, right? You got A, B, C, D, E, F, and G. What happens if I do a two-letter password? Well, now I have 26 times 26 different possibilities, which is, AA, AB, AC, AD, like etc., up to BA, BB, BC, all the way down to ZY, ZZ. And if I do three letters, I have like, 26 times 26 times 26 passwords, right? And it goes on like this, such that every single time you add a digit to your password, you are adding 10 times more different passwords that it could be. And therefore, every single time you add a digit to your password, it gets 10 times harder for a computer to crack it because of just the sheer amount of time it takes. So like, you think about this. Let's imagine for a second that a computer can crack, that it can hash, for instance, right? Like how many times a second could a computer do this, right? Convert a string into a hash. Let's say that it can do a 10,000 a second, right? That makes sense. So then you think, okay, well, how long would it take it to do a one-digit password, right? Which is 26 to the power 1 possibilities. Well, that would be, I'm just like doing some math here. That would be 26 divided by 10,000. So 0.0026 seconds. What about a two-digit password, right? Which is 26 to the power 2. And we'll just like quickly demonstrate. Oops, that's not what I wanted to do. Well. So if I just very quickly demonstrate this, right? Now you have like, what's 26 times 26? I should probably just put this into Google, actually. That's probably going to be easier for me. So I'm like, okay, 26 to the power 2 divided by 10,000 gives me 0.0676. 0.0676 seconds, right? And we can kind of carry this on pretty quick where we say, for a 3-digit password, it's going to take, 1.75. It's not giving me what I want now. 1.757 seconds, right? Like this. And then we could, go to like a 5-digit password. Now, 10,000 a second is an estimate. It could be more than that, right? So now pi, okay. So this one would be like, 118 seconds, right? And like, how long is that? That's like approximately 20 minutes. Okay, and then like you can go up pretty quick. And the point I'm trying to demonstrate here is that the whole point around passwords, 803.181 seconds. And if we go to like, say, 26 to the 10, for instance, we get that many seconds. And it's like, how many hours is 800,000 seconds, right? Seconds to hours. It's like 200, to days. It's like 9 days. Right? And then let's do 14116709565 seconds to years. 447 years. So the point I'm trying to demonstrate here is not that it like literally takes 447 years to crack a 10-digit password, because computers are faster than that, right? 10,000 a second was just an estimate, But the point is, if you have a look at this, the exponential gain, because that's what this is here, right? Like every single time you add a digit, you're adding 10 times more, is quite massive. So, if you have a 10-digit password and then you make that a 12-digit password, it's going to take literally thousands and thousands of years, relatively speaking, for a computer to crack it, right? And also, this is assuming you're only using lowercase letters, right? Which is why we had 26 here. Because if you were using like the full ASCII set, then you maybe might use like, 128. Now, the point of all of this is that this is why hashes are secure, right? This is like why they're safe, because for longer passwords, like there aren't any like rainbow tables out there that have polywaffle pancake. Well, there might be now. Maybe they hash this as you type it in. I don't know. Polywaffle pancake is a secure password because it's not feasible for computers to have figured out every possible 17-character password, right? Yeah, so Catherine says, so when they are trying the 9 days, are they trying to log into your account over and over again? Well, if they tried to, obviously they would get locked out, but this is more like someone might sit there and build a giant Excel file of all the different like possible passwords and all the different hashes. And then when they like say break into Dropbox or Canva or something, they get a whole bunch of hashes, right? Because all the users' data is stored as hashes. And then they get these hashes and then they go, aha, well, this hash is here, so their password might be Hayden. But when they look for the hash of polywaffle pancake, because it's such a long password, they're not going to have had it in their like database. So the takeaways here are that long passwords are secure because it's infeasible to hash all the different types of long passwords. That's why we don't like short passwords. You know, and just generally to you all, I would usually recommend your passwords exceed 10 characters. If you don't have 2FA, if you have 2FA, it's not too bad. But yeah, so the first one is like long passwords matter because it's hard to break hashes. And then generally the second point is that hashes are quite secure because for long passwords, you can't really break them. As in if someone gets a hash, they can't do anything with it. So let's actually apply this now. Let's take this this line from hash.py and let's apply it in Auth. So now when I store my password, instead of storing the password in plain text here, like this, I'm actually going to store the hash of it. So this is just a magical function that I call that will turn a password into a hash. And I'll have to import hashlib because that's the library that I use here. So I import hashlib and then I can hash that password and I'm printing it out after. So now what we're going to do is we're going to go and start auth.py. And by the way, just for those who are kind of watching this and being like, oh my God, this is scary. This is mainly background for this topic. So like, we don't expect you to like be familiar with all this like blah, 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 blah. We're mainly trying to demonstrate that hashing is important. Here's the one line to do it. It's actually very little work to do on this password front. We just want you to understand why you're doing it because that's really critical. So I've started up my server and I'm going to run it. I click send and I store that first username and password. And notice here that I store Claude as the username and the password is this hash. Right? Now, obviously this hash is crackable because the password is a 3-letter word, right? Like your computer could crack all 3-letter passwords in like a second probably. So it's a bad password, but let's pretend for a second that it's a long password that you can't crack. Well, this is good because then again, if you expose this data or someone gets access to it, they don't know what Claude's password is because they can't reverse that hash to a real password. They can, but like pretend they can't. So you think, okay, great, we're all secure now. Okay, that's good. We're storing hashes, we're not storing passwords. This is standard practice in the industry. And then you think, well, how do we actually check if they have the right password? Because now what happens is when Claude goes to log in, as you can see here, oh my God. When Claude goes to log in, or even Claude's son, what's going to be happening is we're going to be taking in Claude's password here, right? Because this will be son. And we're going to be comparing that to the hashed password, right? And that's just going to return false. In fact, it's going to throw an error. And like you'll see this here when I go log in, it's going to say, can't log in because it didn't find the password. Now, obviously, like, and I know someone will tell me probably quite soon, but it's like, the problem here is you can't decrypt this password. So if you can't decrypt this magical string, how can you compare if it's equal to son? Like, how do you know, like, and it's a question, someone will answer it again, but like, how do we do that? How do we check if Claude entered the right password? How do we, like, because if we don't know what that hash is, how can we check if it's son, if we can't decrypt it? Yep. So what we do instead, that's good. Yeah, so you're all on the right track, which is awesome. So what we do instead is that when we compare son here, which is the password that Claude entered, when we compare it to the hash, we don't try and do something where we like dehash the hash, right? Like we're not trying to do something like that. We instead take it the other way, which is we kind of hash son, and then we compare the two hashes. So how do we hash things? Well, I might just pull this out into a helper function here where I'll literally just call it hash. And I'll say like it takes in a string or something. So this is a little helper function for us. So now again, when Claude tries to log in, we just compare the hash of his password against the password that's stored. Right, so what that means is that we hash son and we get this like long thing and we compare if those two long things are the same. And that comes back to that question someone asked about like, if it's hashed, how do we have access it? And Miguel says if he sends the hash, then it's just as bad as storing the passwords in plain text. Yeah, I mean, yeah, I guess that's true. So this will work now, right? So if I open up ARC and I try and register, and I'll do Hayden Smith this time. So I register with that. Hayden and that password there's stored. Obviously, Smith's a very short password, so it's already in a rainbow table. Short passwords are extremely easy to crack. But let's pretend that it's secure, because that's why we're doing it. And then we go to log in with that password. You'll see that this now works, because we compared the hash of the password entered at login to the hash of the password at register. And at no point have we actually ever stored my actual password, which is the critical thing here. Any questions about that? Otherwise, we'll move on to authorization. I mean, the short story there is you hash passwords. Like it's a few lines of code. It's not complicated. It's just a few lines of code. It's important you understand why we do it, because it's a very, very relevant, like security is a very relevant thing to everyone. How do you make transmission safe? Transmission isn't really about programming. It's to do with network stacks and HTTPS and stuff we talked about last week. That's not to do with Python or Flask. Okay, cool. So that's authentication. That's all about making sure that our passwords are secure. Now we have the next question, which is how do we actually make sure that how do we make sure that after we verify a user's real, after they log in, that we can know it's them when they make future requests? And what I'm talking about here is this whole topic around the Auth user ID. Because in iteration 1, you all passed in an Auth user ID to all these functions like channels create and channels list. But there's security vulnerabilities around that as well. So as part of authorization, and you could maybe call this authentication, a really standard practice is that after someone logs in, right, like after they type in their username and password, you store some kind of pseudo password that they can store on their computer, which is essentially a shortcut for getting authorized later. An SSH key is an example of this, right? Like, you know how like you had, you like generated these keys when you like set up GitLab and stuff, you like did the SSH key gen and whatnot. That generates a couple files on your computer. And if someone gets those files, right, there's two of them. If someone gets those files, they can actually log into your CSE account without your password. Because what happened is like you had to log into your CSE machine, which is authenticating yourself, and then you created some kind of pseudo password. And a common example that you'll see of these is cookies, right? So you think about, like, if you think about this website that I'm on now, slides.com, as a Flask server, where every single time I load this page or I make another request, it's like I'm calling Flask, I'm talking to Flask. Well, how does it allow me to look at this and edit it? How does it know it's me every time I make the request? I'm not putting in the password every time, right? Like if I was putting in the password, it would make sense, because you're just always entering the password. But I'm not. And a lot of times what you'll actually see is happening on browsers is that, like web browsers in particular, will just be storing, where is it? Storage? Thought it was application. Oh yeah, cookies. Yeah, so you see here slides.com. You can actually see here that there's actually this giant string here. I'm not showing you all of it, but this is actually like this password that gives access to my account. So what happens is that when I log into a website, and this happens for most things, I log in, I give it my username and password, they hash the password, they check if it's me, I'm authenticated now, and then they give me back this giant string that's kind of like another hash. It's kind of like another hash. And this is like basically like a single sign-on password, if you will, a one-time password or whatever you want to think about it as, that as long as I keep sending this to the server, they know it's me, right? So if you have this, you could just go to this website and send this to the server, and they'd be like, oh, hi Hayden, thanks for making more requests. I can see that that's you. I can see that that's you. So this is kind of this topic around authorization, which is like, after you authenticate yourself, how do you keep a system knowing who you are? Now, again, in iteration 1, you did this by, when you called auth register or auth login, you returned their user ID. So if I was the second user to sign up, and then I logged in with like, my username and password, you just gave me back the number 2, my auth user ID, and that's how you knew it was me. And when I called channels list, when I called channels create, you just took that number and were like, oh, hey, user ID 2, nice to see you again. Thanks, Hayden. No need to give me your password. I know what user ID you are. Now, as you've seen in the iteration 2 spec, there is a emphasis here on token. So every time you've seen auth user ID, you can see that it's been replaced by token. Now, there's all these questions around like, what is the token? And that's what we're getting to now, which is, like, what is the token? It's a packet of data used to authorize the user. We could have called it a token in iteration 1 because it's just a packet of data, right? In iteration 1, the token just happened to be the user ID. That's a terrible token. And I would say that there are generally 4 types of tokens that you could reasonably use. One of them is a user ID, right? So when you log in or register, I give you back your user ID, and then whenever you come and want something from me, you say, hey, I'm user 3. And I say, hi, user 3, nice to meet you. Here's all the channels that you're part of, right? We'll come back to this slide. One of the problems, like, someone tell me, like, the problem with a user ID is that it can be faked. So if Miguel has user ID 3, and Miguel's like using your UNSW Dreams application, and he's sending, I want all the channels, I want to send this message, I want to create a channel, and he's sending the number 3 every time as a way of authorizing himself to do these things. The problem is, all that like Matthew needs to do is Matthew needs to just see that Miguel's number 3, and Matthew's like, I'm user ID 7. I'm just going to change that 7 to 3. So when Matthew's now talking to your Flask server, Matthew's just like, hey, I'm user ID 3. And the Flask server's like, okay, because all the Flask server's expecting is just a number, right? It's kind of like taking it at face value. There's no sanity checks. There's no way of verifying it because it's just an integer, right? Like if Matthew says I'm user ID 3, there's no way that the server can be like, oh, prove it, because he's like, well, user ID 3, it's what you gave me when I logged in. So we're going to talk about a topic next, which is JWTs, which stand for JSON Web Tokens. And JSON Web Tokens are a way of saying, like, when someone's trying to log in with a user ID, it's insecure because anyone can just fake your user ID. If they know your user ID, they can just pretend to be you, right? Identity theft, whatever. And that's not secure. So we're going to talk about how to securely give people, their data, right? And this topic's a little bit complicated, and we might have to talk about sessions tomorrow. So let's loop back to these slides after we kind of understand JWTs and can like put it in our head. So what the hell is a JWT? A JWT is a standard for representing information securely between 2 parties, right? It is not a way of hiding information. I really want to stress this. Hashing is a way of hiding information. It's a way of taking a password and obscurifying it so that no one can understand what it means except like the trusted parties. JWTs are a little bit different. They do not hide the data, right? Anything, like when we use this, we are not hiding the data from anyone, but instead we are making it tamper-proof. And this is really the crux here. So when we want to make sure that like people don't fake our IDs, the point is not that we want to hide our user IDs from people, because that's really difficult. The point is that we want to make them tamper-proof. We want to make sure that like if I give you the user ID 3, that no one else can give me that user ID 3, even if they can see it, right? And what we're going to do is we're going to play around with like a little website that basically teaches about JWTs and how they work. Well, it's more like you get to play around with it. And again, I just want to stress here, because I know there's like the handful of people who are like panicking right now, and they're like, I don't understand this. We go into a lot more depth in the lecture than you need to use for this stuff so that you can understand it, because you understanding it is quite key. So what is a JWT? A JWT is a string. And that string is basically a whole bunch of ASCII characters. And your computer, your browser, like your Python, they're all capable of converting an encoded JWT into a decoded JWT, right? So the encoded JWT is just a whole bunch of scribbles. It kind of looks like a hash, except you can decode it, right? So how does this typically work? Well, you have a server, right, over here, and that server will typically say, I'd like to send some information to a client, right? Which is like maybe a web browser or something. And what that server is going to do is it's going to have a whole bunch of information like this, and it's going to say, I want to package this up in a secure way. Not a private way, in a tamper-proof way. Not in a private way, but in a tamper-proof way. So it wraps all of this in a JWT. And then it sends that. And then the client can decrypt that, decode that, and they can get all that information. And then if they want to, a client can send this back to the server later as well. They can send that JWT back to the server. So let's have a play around with this. Like a JWT is made up of 3 key parts, right? The first part is a header. The second part is the payload, and the third part is the signature. Now the header is really uninteresting, and it basically doesn't change. This is like the start of a lot of JWTs. It gives some information about how it's encrypted and what it is. You don't really need to worry about that at all. The payload is the actual information that you're sending, right? And the verify signature is what makes it tamper-proof. And we'll come back to that in a sec. So notice this, right? If I change this and I add like more information here, watch how this updates the left-hand side. So how to imagine this right now is if I'm a server, I'm on the right-hand side, I've got all this information, and I want to send it to you, right? So if I'm on a Flask server right now and someone's just logged in or they just registered, I don't want to just send them a user ID for their name. I want to send them a JWT. So I'm going to start with what's on the right-hand side, and I will be encoding it. So all this stuff up the top largely stays the same. And then what do I want to send back? Well, I want to send back a auth user ID from iteration 1. And maybe that auth user ID is 4, the number 4. And notice how every time I change this, it like changes the little encoding thing here. Right? See how every time I add stuff, it basically like changes what the pink stuff is. And that's because all that's happening is this thing on the left here is just an encoding of what's on the right. Okay? It's just like converting it to, like, think of like converting it to another language or compressing it. You can convert it back. You can uncompress it. It's just me representing it in a more concise fashion. Now here's the tricky bit. The blue part here is called the signature, right? And the way the signature works, this actually ties in really well to what we just learned, which is the way the signature works is that it takes the header, it takes the payload, and then it takes a secret and it concatenates them all together, and then it hashes that whole thing. So what I mean is, let's imagine for a second that, like, you know, like our header is like, I'm trying to think of an example. It's like, let's like, you know, from the lecture we just did, that if you try and like hash, like if you try and SHA-256 hash Smith, you're going to get like some gibberish thing, right? But what we're doing here is we're actually going to hash the header, which might be like, let's just say it's like AUG HS256 type JWT or something. And then we're concatenating that with our payload, which might be like auth user ID for hello, whatever. And then we hash it with our secret. Now, what's our secret going to be? Let's come up with a secret. Let's use polywaffle, because that's a random name. And then our secret is polywaffle. Now, have a look at this. If I was to like dump this into like one of these SHA-256 generators, you see I get some random hash out, right? So that's what the signature is. The signature is literally just you taking the header, you taking the payload, and you taking the secret and hashing it into this thing. So this is just a header. This is just a payload. It's not encrypted. It's not secure. It's literally just translated. It can be decoded. You don't need anything for it. And then this is the signature, right? And the signature again is the hash of the header, the payload, and the secret. Now, what is the secret? The secret is a string that only the server knows exists. So no one ever knows the secret. Not any user, not in under any circumstances. It's totally a secret. And the secret on the server is what helps make sure that no one can tamper with the JWTs. Now, I know that sounds very conceptual, so let's actually talk through this again a bit more, which is like, watch what happens when I change the secret. If I change this from polywaffle to polywaffle pancake, notice how every single time I change the text here, the signature changes. And that makes sense because you know that every single time you update a string, the hash changes, right? Like we saw this happen where like we typed in like HAYDEN. Notice how the hash is different every single time. And it's the same thing here. When I update my secret, the hash here is going to change. Now, again, this is going to be confusing for a lot of people. And you might have to watch it again and again. The details of this are not critical. And we will have to talk about this a little bit tomorrow too, realistically. So, for something like this, let's imagine that you're a server, you've got this algorithm, you've got my auth user ID, and you want to send me this data. So you're like, okay, I want to send you a JWT. Here you go, Hayden. Here is your token. So instead of sending you a dictionary, instead of sending you back a number, which is 4, right? That's what you did in iteration 1. You sent back a number. That was just your auth user ID. Instead of that, I'm going to send you the JWT, right, which is the encoded version of it. Now you might be thinking, oh, that looks like a hash, so that's a secret, right? It's not like a hash, because a hash you can't decrypt. But watch this. If I'm someone else, right, I'm just going to open this up in another tab. Let's imagine that imagine that this number 4 is Miguel, right? So Miguel is the user number 4, and I get Miguel's JWT, right? And I think, sorry, my bad. Let me explain this. So say Miguel's user number 4, and he gets this JWT from our server. And Miguel grabs this JWT and he goes onto the JWT website and he dumps it in here. And he goes, oh my God, I can see the structure of it. I can literally see what the server's expecting, right? So in this case, I pasted this in here and it's decoded it to what's on the right. And he thinks, oh, I know what I'm going to do. I'm going to try and pretend to be, Michael, who's user ID number 5. So Miguel comes along here and he tries to change auth user ID from 4 to 5. Now this makes sense, right? Because this is what you would do if you were trying to hack someone normally, right? Like if you called auth register and it gave you back a user ID of 4, you might think, oh, I'll type in 5 or I'll type in 3. Like I'll type in someone else's user ID and just send it to the server so they won't even know, like I'll just pretend to be them. So if Miguel tries to do this here and tries to change the user ID from 4 to 5, here's the problem. If you don't have the secret, you can't get the right signature. Because like when the server created this, right? When the server created this token, polywaffle pancake, there was this signature attached to it. Right? And it's like, this is the signature that's like tied to the hash of the payload and the secret. So the point is that like if someone changes the payload, they don't know how to generate a new hash, a new valid hash, because they don't have the secret. Right? So even though like Miguel here has tried to change this auth user ID to 5, the problem is he doesn't have the secret. So if he puts in any random secret like hello, notice how the signature is different. And in fact, let me just pull up these two tabs side by side here. Notice how like even if so Miguel takes this and he gets the JWT. He sees the user ID is 4, so he changes it to 5. Notice how similar these are. Notice that the head is the same between the two. Notice that the payload is the same between the two. But notice that the signature is different. Because if you tamper with the payload and you don't have the secret, you can't generate a valid signature, right? Because the signature is the hash of the payload and the secret. Do you know what I mean? So you need both of them to generate a valid hash. So what happens is I gave Miguel, if I'm the server, I gave Miguel a valid hash because this is a valid hash when you hash the secret with the number 4. But the problem here is that if I change that to 5 and I don't have the secret, I can't generate another valid hash. And that's how servers tell whether a JWT has been tampered with. So let's just quickly like go through an example here, because we've got about 10 minutes left. And have a look at how this system is currently decoding things, right? So what happens is that, and in this case, we'll have to use the username as, oh no, that's not good. We'll have to use the username as like the auth token. So in iteration 1, you use like auth user token. In this case, we're going to use just like the username. So what happens is when I register, right, if I start up this Flask server, when I register, I get given a token, which is just the, which is just my username. Oops, sorry, wrong port. Send. Should work. Port 5000 / register. Seems to have worked. I'm confused. Oh no. ARC is freezing. We might have to reopen it. It's the worst time for it to start freezing. Oh no. Terrible. Terrible, 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 terrible. Oh no. This is bad. That's okay. We'll give it like 10 seconds. So what happens now is instead of sending, instead of like your server sending an auth user ID back to your user, and when you receive a call from on a route, instead of accepting some user ID, you're going to do the exact same thing, except you are going to be sending a token and getting back a token, right? So instead of sending a user ID, you're just sending a token and you're getting back a token. And the whole point of the tokens, again, is that they're tamper-proof. So even if you don't understand any of the stuff I showed you, right? Any of it. The point is that there's a library out there that can effectively let you send data to someone and know that they can't change it, right? Like they can't change it without it becoming invalid. And if they change it and it becomes invalid, you'll know that they tampered with it. So it's basically just a tamper-proof way of sending a user ID, which is super powerful. So I'm just opening up ARC now and we can try this out, hopefully. But let's try and modify the code first. So let's actually take some code from the lectures and modify it. So you can see here, this is actually how we would, I'd love to show you this, but with VLab, it's like, this is how we would decode and encode a JWT. So first thing, we have to import the JWT library, because that's the library that allows us to encode and decode these tamper-proof payloads. The next thing is we're going to have a secret. Now, in reality, a secret should be something that's super long, like as long as a long password, even longer. But in this case, I've just got a secret of senpai. Now, god damn it. That's so weird. Now, what I can do is I can actually encode a JWT by calling this function here where I say I give it a payload, right? This is my payload. I could be anything I want. It could be a list, a dictionary, a list of dictionaries, a dictionaries of dictionaries of dictionaries of lists. It doesn't really matter. And then I just give it the secret, right? And that's all you need to do to encode something. And we can actually play around with this in, I'll do this in Sublime here, where if I open up, actually I'll just copy it in, web token. Oh, it's already here. So I've got this file called web token. And what I'm going to do is I'm going to simply run Python 3 web token. And you'll see that what this actually does is it encodes this data structure with this secret into a JWT, right? So this is what you would do when you call login and register. And you give this back to someone. And then every single time they call one of your other routes where you expect a token, this is your token. It's the encoded JWT. In fact, let me just call this token. So in auth register, you call JWT encode, you give it a payload, it's going to spit out something like this. I'll show you what it spits out. It's going to spit out something that looks like a JWT. This like blah, blah, blah kind of stuff. And you could literally take this, right? And you could paste it into a web thing and you could see what's inside of it. Username Hunter. It's like right there. It's not hiding it. It's not encrypting it. It's simply making it tamper-proof. Okay, so it's always public data. You wouldn't send passwords in JWTs. It's not designed for hiding things. It's designed for tamper-proofing things. So you can see that I'm encoding that into my structure, and then this is what a user would get when they call login or register. And then when that user wants to call channels create or some other routes, they just give you that token back. They just give you that JWT back, and you say, oh, thanks for that token. And then you try and decode it. And when you call JWT decode and you give it the token and you give it a secret, the Python library will give you that data structure. Right? So you can send a data structure to the user, which might, again, I'll just like give you an example. It might just be like user ID, might be like 4. You can send that to them. They can send you that back on other routes so that you can tell who it is, but you know that it's tamper-proof. Because you know you sent this to them, and the way all this maths and the library works means that it has not been modified. And we could apply the same thing here, where instead of returning a username here, we could return a token, right? So like a username can be tampered with because all you need to do is know someone else's username. So let's instead send back a JWT token. In fact, let me just abstract this into a separate function. I'll call it like token encode. And I'll say like username. And what I want this to do is return me a JWT that does this. It like has a little dictionary with just a key, which is the username, and a secret, and it's just going to return that. So instead of the username, I'm going to encode that into a JWT like this. And then I'm going to do the same thing here. So whether they log in or whether they register, I'm going to give them back a JWT because I know they can't tamper with it. And then when someone tries to call another route, like channels create, channels list, message send, where they give me a token, right? I'll say like token here is equal to request.args or something. What I can do is I can figure out like who is this, and I can simply use the JWT decode here, where I say, you know what? I would like to decode the token. And this is the algorithm I want to use. And you know what this will give me? This will give me the data structure. So like what does JWT decode do? It gives you the structure that you encoded. And what structure did I encode? It's right here. The first argument of the encode. So, you know, then if I wanted to like figure out who the user is, I could print like data structure username like this. So again, JWTs, they're not doing anything differently. You're sending some data to a user, and then you get that data back, just like the auth user ID. It's just that you know it hasn't been tampered with because of the power of that library. And the only things you need to do for your iteration 2 are basically like these 3 lines here. You need a secret, and you need to decode and encode them. That's it. Like all this stuff I've shown you on the websites, this is all just to get you to understand what's actually happening, because it's not fun to teach you things and be like, just use this. You don't need to know what it is. So that's actually what it's doing. It's making it tamper-proof. And similarly with the password hashing, all you need to do is actually hash the passwords. So this whole lecture for like an hour and 15 minutes, even though we talked about a lot of concepts, in reality, it's actually only going to be like, for many of you, you know, a dozen or 2 dozen lines of code in your entire project. It's actually a very small thing to do, but it's very important, and it's even more important you understand why we're doing it. Yes, so if I go back to this table we had before, we can send a user ID as a token. It's just insecure. If we send a user ID wrapped in a JWT, it's now secure. What we're going to talk about for 15-20 minutes at the start of tomorrow's lecture is a topic around how to have multiple login sessions at once. Right? Because one of the problems with sending back a user ID is that you can't really distinguish between, like, you log into Facebook on your phone and you log into Facebook on your laptop, right? And when you call log out, right? If you say, I'd like to log out of Facebook, if what you're sending to Facebook is a user ID, if you're like, I'm user number 4, please log me out, Facebook is like, okay, so it basically, like, what do you even do there? You basically say that no one using any devices can log in again. So one of the last pieces of this topic is essentially just talking about, and it's just a little bit of a code demo, is how do you have it so that you can have multiple people logging into your application at the same time? Which is pretty much everything we learned today, except instead of storing and sending user IDs, we send session IDs instead. And that's this whole topic. It's hash your passwords, encode and decode your stuff with JWTs, and then tomorrow we'll talk a little bit about using sessions instead of user IDs. So yeah, lot to take in. And I just stress for like the 5th time, because no matter how many times I say it, people still get worried. All of this stuff where we went through like the hash tables and the Excel spreadsheets and the all this little math I did in the file here, and the JWT things. It's like all of this stuff is not core content. You aren't going to be expected to do any of the things I just described here today. It's all just about trying to help you understand what is a complex topic, but one that is critical, is not too much of a black box to you. So that's pretty much all I have for today. Let's keep chatting about this tomorrow, and we'll get on to some other topics tomorrow, because we got some other short lectures around some software engineering principles, and then just a very short thing on persistence. So yeah, thank you everyone. It's been fun. So chat next lecture.